Welcome to the Algebra 2 Chapter 9a review video. So comparing our work here, we've learned some new things with radian angles, some reference angles, as well as some familiar content, just extended those ideas of right triangle trigonometry, the concept of a sine, cosine, and tangent function being ratios of side lengths. So now we're just going to go through and take a look at what skills are going to be assessed on this test. So let's have a look. This review guide, I'm just going to say right away, contains some extra practice. The test itself will be a little bit shorter, so kind of like with the Chapter 7 review guide as well. This review is going to be as comprehensive as possible. The actual test will be a little bit shorter just to fit it in a class period. But you can see it opens up with some basic right triangle trig, sine, cosine, and tangent. You have to tie in a little Pythagorean theorem there to make this all work. We also introduced those reciprocal functions, cosecant, secant, and cotangent, just practicing our skill set there with those new functions as well. So let's have a look at the first one. Here we have a right triangle given, and you can see that we've got some angle theta, and we need to find all 6 trig functions of that angle theta. And in order to do that, I'm going to need to know all 3 sides. I've got my angle here, so I'm given an opposite leg of 2, hypotenuse of 2 root 5, and I'm going to have to do some work to find the adjacent side. Now, 2 square root of 5, I know that a squared plus b squared equals c squared, so my missing leg squared plus 2 squared is going to equal 2 root 5 squared. That means a squared plus 4 has to equal 4 times 5, 20. A squared is just 16, and that means that a itself has to be the square root of 16, 4. And just a quick check through Pythagorean theorem, make sure that that holds true. All of our fractions are going to be found, the outputs of those trig functions are going to be found using those values. We want to make sure that those are correct. All right, sine is opposite over hypotenuse. That is 2 over 2 root 5. Okay, obviously the 2's are going to cancel. That's like 1 over root 5, which we know is root 5 over 5. Cosecant, we take the reciprocal of that. If it was 1 over root 5, then its reciprocal would just be square root of 5, and that's hypotenuse over opposite. We can double check. Yes, the 2's will cancel out. That is our answer in simplest radical form. Cosine is going to look just like sine, except instead of 2 over 2 root 5, it's going to be 4 over 2 root 5. And we'll see the same type of cancellation, except the 2's don't cancel. It's now 4 over 2, simplifying to 2 over 1. So my answer should be 2 root 5 over 5. All right, and likewise, secant, that will be root 5 over 2 when we take its reciprocal. Tangent, opposite over adjacent, that one's a nice clean one here. It's 2 over 4, or 1/2. And the cotangent, its reciprocal, 2 over 1. Problem number 2, you'll notice a very similar setup, except here, no triangle. We are given one trig function right away, root 11 over 3 for tangent. I can go ahead and put that one in right now. And I know that cotangent will be its reciprocal, so I can use that right away. That's going to be 3 over root 11, which rationalizes to 3 root 11 over 11. We should be pretty adept at that by now. Well, if there is no triangle, let's construct our own. So I've got some theta whose opposite over adjacent is root 11 over 3. And then to find the hypotenuse, we will use Pythagorean theorem yet again. C squared is going to equal a squared plus b squared. And here we know the legs, so we can plug those in. C squared is going to equal 9 plus 11. That means c squared equals 20. So c is going to be the square root of 20, or 2 root 5, simplified radical form, simplest radical form. So now for sine, what I can do, my opposite over hypotenuse is going to be root 11 over 2 root 5. And the problem is that root 5, so if I multiply that into the top and the bottom, I get root 55 over 2 times regular 5, 10. All right, and if I take the reciprocal of that, well, this is the first time we've worked with two radicals in a problem, so it's a neat opportunity for us here. If I take the reciprocal, I'm going to take the reciprocal of this simpler one and then just kind of deal with that as is. I could also flip this 10, write it as 10 over root 55, but then I'm going to have more simplifying, I think, in the long run, but it will lead me to the right answer. So if I have 2 root 5 over root 11, then the problem is the root 11. So I multiply that into the top, get 2 root 55, and my denominator is all over 11. All right, for cosine, I'm going to see a 3 over 2 root 5 when I do adjacent over hypotenuse. Again, the problem is the root 5, so I multiply that into the numerator and denominator. I can't forget about that 2 that's already down there. It's going to be 2 times regular 5. That will be a 10. For secant, again, I'm going to take that unrationalized version from before, because when I take its reciprocal, I get 2 root 5 over 3, and there's no additional work to be done. And aside from the cosecant, secant, and cotangent, this could be found on any geometry test that you probably have taken last year, or a geometry test in any regular geometry class anywhere in the country, probably. So nice review. Likewise with number 3, solve the triangle, round all answers to the nearest hundredth. Notice that the given angle is degrees, and on the test we are encouraging you to use degrees for these problems as well. Anytime we talk about a real life situation like we see in number 4 with our word problem, we want degrees. That's how we communicate angles in the real world, unless it's obviously based on something with the trig functions we're actually going to graph later on. So stick to degrees for now. So letter A, we're given that the measure of angle B is 41. Using the triangle sum theorem, all 3 of those angles inside have to add up to 180. Angle A must be 49 degrees, and I need to have that degree sign there if I want full credit. Okay, side B is going to be opposite angle B, and then side C will be the hypotenuse opposite angle C. And we're going to have to use trig here to find, well, let's find side B first. I know that the tangent function, if I'm looking from my given angle of 41, the tangent of that 41 degree angle is equal to B over 4. So if I multiply both sides by 4, again, just setting that up using opposite over adjacent, I'll take tangent of 41 times 4, and I get 3.48. And I could use Pythagorean theorem to find that side length C. If I'm rounding carefully, I should arrive at the correct answer that way. But I think trigonometry is a little bit faster for this as well. I'm given the 41. I know the adjacent leg to that 41 is 4, and the hypotenuse is C. Adjacent and hypotenuse will use the cosine function. So I have 4 over C. So in the calculator, I'm going to do 4 divided by cosine 41 to find that answer, and I get 5.30, or just 5.3. Okay, and if we look at that, yes, it's pretty close to a 3, 4, 5. My hypotenuse is the longest side, so the answer makes logical sense. For letter B, here it's kind of guiding us with these blanks to find the angles first, and really as soon as we find one angle, we've got the whole thing pretty much handled here. So I need to remember that finding the angle means using the inverse. If they're asking for angle A first, I'm just going to go right in order. If I want to find angle A, I know that it has a tangent ratio of 3 over 5. So I'm going to go ahead and use tangent inverse, right? If I'm finding an angle, use the inverse, and I'm going to plug in that 3 divided by 5 for its input. The output angle is 30.96 degrees. All right, and that means that using our triangle sum theorem, if they're all going to add up to 180, angle B must be 59.04 degrees. It's really close to a 30, 60, 90 right triangle, so that math is not too difficult to work out. Lastly, if I want to find side length C, the hypotenuse, I can use Pythagorean theorem here. A squared plus B squared equals C squared. That means I'm doing 9 plus 25 to get c squared, and I'll square root that 9 plus 25, that 34, and I get 5.83 for side C. Number 4, Clark Griswold is hanging Christmas lights. His ladder, ooh, there's a typo. His ladder is 25 feet long and leans up against the front of the house with the base of the ladder at a point 6 feet away from the house along the ground. What is the measure of the angle formed by the ladder at the ground? Answer this in degrees rounded to the nearest hundredth. All right, so here's the house, here's the ground, and here is the ladder. Okay, so if the ladder is 25 feet long and it's 6 feet away on the ground, what angle theta is going to be made at the base of that ladder where it meets the ground? And looking at the available side lengths, I've got an adjacent and a hypotenuse. I know that the cosine of that angle is going to be 6 over 25. Let's find that angle using cosine inverse. So again, to the calculator we go. Very nice, quick problems that we have. We get an angle of 76.11 degrees. Okay. Very steep angle and pretty indicative of what we saw in the movie Christmas Vacation when he falls backward on his ladder against the tree. Hilarious. So those first 4 problems, I would consider that to be section 9.1, refamiliarizing ourselves with SOHCAHTOA from geometry and also how to solve real-world problems using inverses and those ratios. Now we move into 9.2, where we learned about radian measure and drawing angles in standard position. How do we take this geometry concept and put it on an XY plane to bring it into algebra? So remember, each one of these angles is going to start on the positive x-axis for an initial side, and the direction that we are turning to place the terminal side in place is given by whether the angle is positive or negative. So in the case of letter A, it's a negative angle. I'm going to measure clockwise, move into a quadrant with negative values. So 510 degrees, well, 360 is a full circle. I need to go another 150 degrees to create negative 510. So there is my terminal side, and I'm just going to label that as 510 degrees, and my arrow of rotation showing us that it's negative. For letter B, 3 pi over 4, there's my initial side. Remember that 180 degrees is the same as pi radians. We're given a pi radian angle, a fraction of pi, so I want to go 3/4 of the way to pi to create that angle, and I'm indicating that it was drawn in a positive direction. Letter C, negative 7 pi over 2. Well, every time I rotate to an axis, that's 1 pi over 2. So I'm going in a negative direction. 1, 2, 3, 4, 5, 6, 7 pi over 2s to end up at that terminal side. Letter D, 8 pi over 3, same idea. If this is pi radians and a full circle would be 2 pi, well, 2 pi would be 6 pi over 3 if I got a common denominator. So there's 6 pi over 3. Then I want to go 2 more thirds of the way to another pi. There's my terminal side. 8 pi over 3 radians measured in the positive direction. Letter E, 200. Well, now we're back into degrees. I go 180 degrees and then 20 degrees further. I end up down in quadrant 3, and I'll label that. What I'm looking for when I'm grading these, are we getting to the correct quadrant, and are we making an accurate assessment, a good estimate on how far into that quadrant we are going to go? So lastly here, letter F, 13 pi over 6. It's a positive radian angle. I start on the positive x-axis. Let's see, 12 pi over 6 would be 2 pi, and I'm going a pi over 6 further into quadrant 1. And I will label it as such. Now, if it's more helpful to you to convert everything to degrees, we've learned how to do that. By all means, go ahead and do that if that helps you draw the angles. More power to you. Like I said, what I'm looking for is, are we ending up in the correct quadrant and approximately the correct amount into that quadrant? Number 6, convert from degrees to radians or radians to degrees. And then we're told that letter C should have a decimal answer. So letter A, 160 degrees. Well, our common ground between degrees and radians is the fact that 180 in degrees is the same as pi in radians. So I start off with 160 degrees out of that common ground 180. That equals some number of radians out of pi radians. To solve for x, I would simply multiply both sides by pi and simplify the fraction. 160 divided by 180 is going to be 16 over 18. That's 8/9. So I've got 8 pi over 9 for a radian angle. And again, some of that simplifying fractions could be done in a calculator if needed. For letter B, here I've got negative 13 pi over 8. That's my angle out of pi. That equals some number of degrees out of 180. And to solve for x, here I'd multiply both sides by 180. All right, so what's happening over here? There's quite a bit going on. I've got negative 13 pi over 8, and then to divide by pi is like multiplying by its reciprocal, 1 over pi. Essentially, it just cancels the pi out of the entire operation. Okay, and then can't forget I'm multiplying by 180. Okay. So negative 13, I'm going to turn to the calculator for this. I got negative 13 times 180 and then divided by 8. Oh, and I do get a decimal for this one as well, 292.5. And I converted that to degrees. I better put my degree symbol there. Letter C, I've got negative 4. There is no degree sign there at the onset, so that is a radian measure. So negative 4 in radians over pi equals some number of degrees out of 180. Let's multiply both sides by 180. I find that that angle measure, I don't need to say x equals there. We're not solving an equation. So let's see what we got. 4 times 180 divided by pi, just using the calculator for that, 229.18 degrees. And that was a negative angle. I don't want to leave that off. And actually looking back to letter B, that was a negative angle. I forgot to put that negative sign in there. That should be there as well. Number 7, find a positive and negative angle that are coterminal to the given angle. Well, here we want to add and subtract a full circle. That's going to be that terminal side rotating through an extra time to create the exact same angle that we began with. All right, so letter A, here I take my negative 78 and I will add 360. That will bring it to a positive position. And when I do that, I think I get 282. Let me check. Yeah, 282 degrees. Of course, I want to put the degree symbol on my final answers, of course. And then subtracting 360 will take that further negative, giving a negative coterminal angle. And there I get negative 438 degrees. For letter B, here I'm trying to add and subtract a full circle of radians. That means I'm adding or subtracting 2 pi. And to add and subtract a full circle of 2 pi, I need a common denominator with these fractions. So 2 pi is the same thing as 10 pi over 5. That sets up that common denominator of 5. So I'm taking my 9 pi over 5 plus 10 pi over 5. I get a positive coterminal angle of 19 pi over 5. And if I take that 9 pi over 5 and subtract 10 pi over 5, a full circle, I get negative 1 pi over 5. And lastly, letter C, this is a very, very positive degree measure right now. So if I want to find another positive coterminal angle, I can start subtracting 360. And if I subtract away 360 from 810, I get 450 degrees. There's a positive coterminal angle. It's smaller, but it's still positive. And if I take 450, take away another full circle, I get back to the same spot. Well, that's 90 degrees. It's another positive coterminal angle, so that could be a possible answer, but I haven't gotten a negative one yet. So I take that 90 degrees and I subtract 360, and I get negative 270 degrees. Now I've got a negative angle that's coterminal with what I began with. So again, kind of on theme with what we've been doing so far this chapter. Not necessarily difficult work or lengthy work, but just a lot of quick calculations, and minor details like degree signs have a huge influence. So we want to be sure that we are cognizant of those. Number 8 says find the reference angle theta prime for the given angle. Letter A, 712 degrees. Well, I'm going to start by drawing it in standard position. A full circle is 360. A second full circle would be 720, so I'm stopping just short of that. There's the terminal side. Okay, to draw the reference triangle, I connect that to the positive x-axis, and notice that that angle is going to happen between that positive x-axis and my terminal side. So I'm asking myself, okay, how much more do I have to go to make that second complete circle? So that theta prime inside is going to be, well, if I got to 720, that would be a complete circle. Take away the 718 that I did rotate, or sorry, 712 that I did rotate, I get 8 degrees. And you don't need to show that work. All I need to see is the angle being drawn, and then how did you arrive at your answer? Just, you can use a calculator for that. Letter B, 9 pi over 4. Well, if I were to go 8 pi over 4, that's a complete circle in the negative direction. I need to go an extra pi over 4. So there is my angle drawn in standard position. And if I connect that to the positive x-axis, there's my reference triangle. Reference angle, of course, happening inside at the origin. And this time I'm connecting it to the x-axis. It's like, hey, how much did you overshoot that 2 complete circles? So my 9 pi over 4, what's the difference between that and the the complete circle 2 pi, which is also 8 pi over 4? I find that I overshot it by 1 pi over 4. And as I said earlier, you're more than welcome to convert this to degrees if that makes the math easier to either draw the angle or calculate the difference. Just be sure that if we're starting with a degree measure, our answer is also a degree measure. And same thing with radians. If we start in radians, we should end in radians. For the next section, use a reference triangle or the unit circle to evaluate the following trig functions. Here, if we're going to be successful, we have to know the ratios of the sides of a 30-60-90 and a 45-45-90. So for letter A, let's start by drawing 150 degrees in standard position. Okay, let's draw our reference triangle in there, and our reference angle inside, theta prime, is 30 degrees. That's how much further I'd need to go to make it to the axis. And if that's a 30-degree angle, I know that the side lengths are the side lengths of a 30-60-90. 1 to root 3 to 2. And that root 3 leg is going in the negative direction. Now I can evaluate. I'm using my reference angle. Surprise, for reference, opposite over hypotenuse is 1/2. For letter B, here the tangent of an 11 pi over 4 radian angle. Again, 8 pi over 4 would be a full circle. That's 2 pi. And I want to go 3 more pi over 4s. So I'm going to end up over here in quadrant 2. If I draw in that reference triangle, connect it to the x-axis, inside my theta prime is a pi over 4. I would need to go one more pi over 4 to get to the axis, one more measure of 45 degrees if we want to think in degrees. And furthermore, the side lengths in a 45, 45, 90, which is what we just constructed, 1 to 1 to root 2, and I'll make sure that there's positive or negative signs indicating the direction of each leg. And the tangent here, opposite over adjacent, is 1 over negative 1. So that tangent simplifies to just negative 1. Letter C, cosecant of 2 pi over 3. I'm going 2/3 of the way to pi. Oh, I didn't realize we had 3 examples in a row that end up in quadrant 2. All right, if I construct that reference triangle, the reference angle inside, theta prime, is the 1 more pi over 3 radian angle I'd need to get to the axis. Okay, if that's pi over 3, that's the same as 60 degrees. I've got a 30, 60, 90. Let's label those leg lengths. And the cosecant is hypotenuse over opposite. So I've got 2 over root 3, which is 2 root 3 over 3 once it's rationalized. We want exact answers here, no decimals. Letter D, cotangent of negative 5 pi over 2. Well, let's draw that in. Negative 1, 2, 3, 4, 5 pi over 2. Oh, I fall directly on an axis there. That means I'm going to use the unit circle and this point of reference, 0, negative 1. Because the cotangent there, well, tangent is y over x. If we think about the unit circle, cotangent would be x over y. And in this case, that's 0 over negative 1, so that cotangent is 0. No reference triangle needed, because we can't construct one. Letter E, secant of negative 225. Let's draw it. Well, that's 180 in the negative direction and another 45 degrees. So we're here. There's a surprise, yet again in quadrant 2. If I construct that reference triangle, here I see I overshot the axis by some amount. So to find my reference angle inside, how much past 180 did I go? Well, that's 45 degrees. 1 to 1 to root 2, we've made a 45, 45, 90. Need a negative sign there because that leg on the x-axis is going in the negative direction. And the secant from that reference triangle will be hypotenuse over adjacent. So it's root 2 over negative 1. That's negative square root 2. And lastly, cosine of 120 degrees. Draw that in and end up in quadrant 2. This is not something that you should be expecting to happen on the test. It's just kind of a matter of coincidence that the problems generated show this. Construct our reference triangle, just like the one directly up above it. We're left with a reference angle inside that is 60 degrees. So we'll label the legs accordingly. And the cosine of that, adjacent over hypotenuse, negative 1/2. Okay, obviously we want to be sure that we end up in the correct quadrant and that we label the sides. We have to know those ratios every time we make our reference triangle. If it's a special right triangle, we have to be able to label that ourselves. Otherwise, we won't be able to answer what's adjacent over hypotenuse, opposite over hypotenuse, things of that sort. All right, and the last type of problem that we covered, this is our bonus section, solving a trig function from 0 to 2 pi. So for letter A, our task, first of all, is to isolate the trig function. That means dividing both sides by 4. I don't know why I put 2. Divided by 4. I find that the cosine of x then equals negative root 2 over 2. Oh, that looks like they rationalized 1 over root 2. And if we can catch that, it makes it much easier to spot what type of special right triangle we may or may not have. All right, so if I draw that out, let's see. My cosine is negative. That means the x values are negative. My reference triangles are off to the left. And adjacent over hypotenuse is 1 over root 2. Oh, I can tell 1s and root 2s. Inside, I've got reference angles that are 45 degrees. And since we're talking about answers that fall in an interval of radian measure, pi over 4s. So to answer the question, what angles lead me there? Here I stop pi over 4 short of a full pi. That would be 3/4 of the way. And the other solution, there I overshoot the axis by one of those reference angles, 5 pi over 4. Let's turn to letter B now. If I'm going to isolate the trig function, I need to add 3 to both sides. 4 sine squared of x equals 3. Divide both sides by 4. Sine squared of x is 3/4, and then square root both sides. That means sine of x equals plus or minus square root the top, square root the bottom, root 3 over 2. So I'm asking, where can sine be positive or negative? Well, sine could be positive here, sine could be negative here, negative here. Oh, I've got a reference triangle in all 3 quadrants. And that's opposite over hypotenuse at every single juncture there, remembering that the reference angle is happening inside at the origin. So that reference angle theta, I just notice I'm using thetas when my variable is x, so that should actually end up being x equals 3 pi over 4. Over here, my reference angle theta prime, every time I'm inside one of those triangles, it's a 60-degree reference angle, pi over 3 in radians. All right, so what angle leads me to each solution? Well, if I start on the positive x-axis, what leads me here? That would be pi over 3. What leads me here? That would be 2 pi over 3, right? Just falling 1 short of that axis. I go here, that would be 4 pi over 3, just overshooting the axis. And the final one, falling 1 pi over 3 short of a full circle, 5 pi over 3. And our final two, it's not going to be as easy as just doing a simple algebra calculation. Sometimes we'll have to factor. I'll have to set up multiple drawings here. And we'll see that in letter C. Here I can take a GCF of, I believe this is a typo. Yeah, this is a typo. It's supposed to say equals 0. I can take a GCF of cosine out. So then I'm asking, where does the cosine, that first factor, equal 0? Remember, cosine means left or right. Where can there be reference angles that have no left or right movement? Well, it's on the y-axis, and that happens in 2 places. So that gives me solutions of x equals pi over 2 or 3 pi over 2. The other factor is telling me, where does tangent equal positive 1? Well, remember, tangent means slope, so I got a positive slope here, 1 over 1, opposite over adjacent, and also down here, opposite over adjacent, negative 1 over negative 1. And here, that reference angle inside is a pi over 4, 45-degree triangle. So the solutions I get out of that are pi over 4, and then overshooting the axis, 5 pi over 4. And our final problem here, we can see the trinomial. We got a squared sign, a regular sign, and a constant. Let's get it set equal to 0. Again, since it's a trinomial, I want to factor that. All right, the first factor is saying, where does sine of x equal positive 1/2? Well, positive sign could occur anywhere the triangles have positive height, quadrants 1 and 2, opposite over hypotenuse, opposite over hypotenuse. Hey, that reference angle inside is a 30-degree, pi over 6. So I get a value of 1 pi over 6 to lead me to my first triangle, and 5 pi over 6 to lead me to the second. Second factor says, where is sine x equal to negative 1? That's saying where is it all negative height? And the only place that can happen is down here when x equals 3 pi over 2. So there you have it. I apologize. It did go kind of quickly. If you have any questions over this, don't hesitate to ask me. But really, a lot of really cool concepts that are definitely going to prepare us for the next year pre-calculus. So happy studying and good luck on this test.